Hi, Math 1B. We are embarking on a new kind of concept here. Well, not a new concept. You guys saw it in Chapter 3. But we started out this whole remote learning thing talking about exponent properties. Then we moved on how to deal with polynomial multiplication, addition, subtraction. We did some stuff with systems of equations to kind of review the thing that we just left off with before we went towards remote learning. And now we're going to jump into factoring. Okay, so it's been a while since we've talked about factoring, so it's a perfect time to reconnect with that concept. So the first lesson I'm going to talk about is how you find the greatest common factor and successfully factor a polynomial. So here's what I mean. So this right here is a polynomial. We've done some stuff about addition, subtraction, multiplication, all that good stuff. Factoring is basically doing the reverse of the distributive property, creating multiplication between two factors that ultimately will help us solve equations later on. And you guys might see that before the end of the school year. So here's what we got to do. We have to determine what the greatest common factor is, because that's the thing that both of these parts are going to share. And we're going to kind of like undo the distributive property. Remember when we got rid of parentheses? Now it's like we're creating parentheses, separating the greatest common factor from its, I just call them leftovers. So let's check this out. 45x plus 36xy. What we can do is individually analyze 45x and 36xy in terms of prime factorization. So if you think back, prime factorization involved the factor tree, which means taking something like 45 and breaking it down to its smallest components, its prime factors. So if you know prime numbers, they're numbers that only divide 1 in itself. So even numbers aren't prime. Let's break it down. 45 can't divide 2. But it can divide 3. So when you take 45 divided by 3, you get 15. You can break 15 down again by dividing, can't divide 2, but it will divide 3. And 15 divided by 3 is 5. So we got the basics, the nuts and bolts of what 45x is. 45x is 3 times 3 times 5 times x. And I'm going to put a 1 every single time we do this prime factorization business. And I'll only circle the 1 if all the factors, if the only thing they share is that 1. Okay? So this might seem like ridiculous. Why are you putting the 1 on there? Hopefully you'll see why in some future examples. All right, so check out 36xy. When you break 36 down, it is even. If they're even, just keep cutting it in half, all right? That way, all the prime factors will be sort of like on the left part. So 2 times 18. 18 still even. 2 times 9. And then 9 is just 3 times 3. So 36xy is 2 times 2 times 3 times 3. So notice we're not including any numbers that were factored down. We're not including that, we're not including that, we're not including that, or that, or that. It's just the prime numbers in there. And there's an xy, so I'm just going to put times x times y. You should always expand the variable expressions if you're using prime factorization. And then put a 1 on the outside. Now the actual factoring of the polynomial looks like this. You are extracting, you're taking out the GCF. They share a 3, a second 3, and an x. That represents what the greatest common factor is. So they share 2 3's. So you're going to say it's 3 times 3 times x. It's 9x. Now, the leftovers, students can get confused by this. It's whatever holds the place that 45x did, and then whatever holds the place of 36xy, and it's creating a new polynomial inside. So if it was 2 terms to begin with, then you're going to have 2 terms for the leftovers. So then, we're left with a 1 and a 5. So you take 1 times 5. And that's the placeholder of the leftovers for 45x. Now you do the same thing for the 36xy. You get 1 times 2, which is 4. And then there's still a y that was not connected to the other one. So it's 4y. And then there's addition between them. Remember, I don't want to just glob them together and multiply. It's not 20y. It's 5 plus 4y. And that's our factored polynomial. Let's try another one. So if we use prime factorization, like we did the first time, I don't think I need to use a factor tree for 9, because 9 is just 3 times 3. And I'm going to include the 1. And then b squared, call it bb. C squared, call it cc. All right, and then we have minus 27b to the third, c to the fourth. All right, so maybe we should do prime factorization over here on 27. Well, we probably could do that in our head, which is 3 times 9, which 9 is 3 times 3. All right, so it's a trio of 3's. Three of them. And then I'm going to include a 1. And I'm also going to include a negative 1 because there's a negative on the outside here. 3 b's and 4 c's. All right, circle what they share, except the ones. The ones, we're just going to leave them as they are. So they share a 3. They share a 3 again. They share a pair of b's twice. And they share 2 c's. So my greatest common factor is 3 times 3 times b times b times c times c, which ends up being the entire term there. It's 9b squared c squared. Now for the leftovers, remember, we need a placeholder for both parts. So it seems like we totally decimated 9b squared c squared, like it's all gone. But see how we didn't circle the 1? That reminds us that it always has a 1, even when every part seems to have been taken out with the GCF. So the leftovers for the 9b squared c squared, it's still a 1. For our second term, it's negative 1 times 3, so negative 3. And then there's a 1b left over and 2 c's. There it is. Now, some of you guys like shortcuts. And I'm going to show you maybe a different way of doing this so you don't have to write out the prime factorization every single time. This is very helpful if you're good with mental math. So if you can look at this and ask yourself, all right, just take it one step at a time. What does 50, 5, and 100 divide? And if you can do that, then you can start to figure out what the GCF is without even doing prime factorization. So check this out. If factoring is the greatest common factors on the outside and the leftovers are on the inside, you can start immediately finding the GCF by just asking yourself, what is 50, 5, and 100? All of them divide. Well, they all end in a 0 or a 5, which means they all divide a 5. Okay? So, awesome. I'm moving on to the W's now. W squared, W to the 1, and W to the 1. They all have at least one W. Z squared, Z cubed, and Z. They all have at least one Z. That's my GCF. No prime factorization needed. Now the question is, how do we determine the leftovers? Easy. You actually just divide each of these by the GCF to get the leftovers. The reason? You're undoing the distributive property. The distributive property got rid of parentheses through multiplication. You are doing the reverse. So the reverse of multiplication? Division. So 50 divided by 5 is 10. W squared divided by W is W. Z squared over Z, 10WZ. There's our first term. Second term, negative 5 over 5 is negative 1. W over W cancels out, so I'm not going to include a W in that term. Then Z to the third divided by Z. Well, remember, subtraction is how you divide powers, so 3 minus 1 is Z squared. All right. Then you got plus 100 divided by 5, that's plus 20. The W's cancel completely, the Z's cancel completely, so you're left with just a 20 at the tail end of that. All right, I got a few minutes, so I will show the same method on number 4. So you got 65x squared minus 21xy minus 34y squared. All right, these numbers can be kind of awkward, so I might just do the factor tree to do some investigating. So 65 divides 5 and 13. So those are both prime numbers. It doesn't break down any further than that. 21 is 3 times 7. So this is interesting. Right away, 2 of the 3 factors don't share anything except a 1. 5, 13. 3, 7. 21 shares nothing with 65, and as you can guess, 34 is just 2 times 17. None of the factors are shared by any of the parts. So what happens when you have basically factors that are not shared? Well, you call that a prime polynomial. Since none of the polynomial's terms share a factor greater than 1, it's prime. So there's kind of a vocab word that you might have forgotten about. A polynomial that is unfactorable is called prime. All right, guys. I hope this video is helpful to you, and you have an easy time going through the 6 examples on the homework. Good luck.